Hello everyone. Welcome to the course Principles and Applications of Mechatronic Systems. I'm your instructor, Jom Shinja. Today we'll study Chapter 2, Fundamentals of Automatic Control, Basic Concepts and Requirements of Automatic Control Systems 1. In automatic control systems, basic concepts and requirements form the foundation for analysis, design, and application. They are crucial for ensuring system efficiency and stability. This lesson focuses on mastering these fundamentals. We will interpret the concepts, explain the requirements, and use case studies to illustrate their application. Take the diagram of a furnace temperature control system principle as an example. The target furnace temperature T0 is achieved by using a timer switch to control the heating of the furnace via resistance wires, resulting in the actual furnace temperature T. The longer the timer switch stays closed, the higher the temperature rises. This reflects the concept of automatic control. Understanding the logical relationships here is helpful in grasping automatic control principles. In the case study comparing automatic motor speed control with manual control. For the manual control system, the process involves the eye observing the speedometer reading, the brain comparing the actual speed with the desired speed and calculating the necessary adjustment to the potentiometer, issuing a command, and the hand adjusting the potentiometer accordingly. This changes the motor's operating voltage, keeping the speed within the required range. Finally, the motor and reducer drive the load. For the automatic control system, the process involves closed-loop detection, amplification of the difference between the set point and actual value, and driving the motor and load to operate at the desired speed. Comparison of automatic and manual control. In automatic control systems, measuring instruments, controllers, and automatic regulating valves replace the human observation, decision-making, and manual operation in manual control. This greatly reduces human labor intensity. At the same time, due to the much higher speed of signal measurement, computation, transmission, and response of instruments compared to human observation and action, automatic control can meet the demands of fast-changing signals and high-precision control, which are difficult to achieve with manual control. 1. What is automatic control? Automatic control refers to a process where, without direct human intervention, a control device enables production equipment or processes to operate according to a predetermined rule, automatically correcting deviations caused by external disturbances. 2. What is an automatic control system? A system that performs automatic control functions is called an automatic control system. The performance of an automatic control system directly affects product yield, quality, cost, and labor conditions. It plays a core supporting role in intelligent manufacturing and intelligent control technologies. Automatic control is indispensable in all fields, including industry, agriculture, transportation, and national defense. Take the water-level automatic control system as an example. Control task: maintain a constant water level in the tank. Control device: the pneumatic valve adjusts the inflow of water. It is the actuator. Controller: regulates the valve based on feedback from the float. It is the commander. Controlled object: the water tank and water supply system. Controlled variable: the water level inside the tank. Each component works in coordination, vividly demonstrating the concept of automatic control and automatic control systems. 3. Components of an automatic control system. Functional block diagram. A functional block diagram is a commonly used method to describe a system, clearly showing how each part cooperates. An automatic control system consists of two main parts. 1. Controlled objects such as machines, equipment, or production processes. 2. Control device, including controllers, sensing elements, etc. Using the functional block diagram, we define each component as follows. 1. Sensing and transmitting devices. Sensors convert process variables into specific signals. Transmitters convert these signals into standardized output signals. These play the detection role in automatic control systems, providing the basis for display and feedback control. Common sensors include those for temperature, flow, pressure, rotational speed, displacement, and other physical quantities. 2. Controller. The controller compares the signal from the sensor/transmitter with the set point of the process variable to obtain the deviation signal. Based on a predefined algorithm, it determines the magnitude and direction of the control signal, which then drives the actuator. Common controllers include intelligent PID instruments, PLCs, computers, control boards, circuit boards, etc. 3. Executive body. The actuator receives the signal from the controller and exerts a direct control effect on the controlled object based on the size and direction of the control signal. Typical actuators include various relays, solenoids, control valves, motors, etc. 4. Controlled variable. Refers to the process parameter that needs to be controlled, such as the water level in a boiler drum, reactor temperature, or material flow rate. 5. Set point. The desired value of the controlled variable in the production process. It can be preset internally in the controller or provided externally. 6. Measured value. The actual value of the controlled variable obtained by the sensing element. 7. Manipulated variable. The variable controlled by the control valve that realizes the control effect and counteracts disturbances is the output of the control valve. 8. Control signal. The value calculated by the controller from a deviation according to a defined rule. That concludes this lesson. Thank you for listening. See you next time.